Hello, I'm going to talk about my attempt to use chemical ionization mass spectrometry to measure aerosolized PFAS in Philadelphia. Here is the chemical ionization mass spectrometer. We call it SIMS. And this SIMS has an ionization source of iodide. This iodide anion forms adducts with incoming species. Here you can see the mass spectrum at peak 341. This peak corresponds to the nominal mass of PFBA. So here we have a voltage controller, which is controlling the voltage to a heating element around the thermal desorption tube. So here is the heating element put around this tube, which we're calling the thermal desorption tube. And this thermal desorption tube carries the nitrogen carrier gas and heats it up. Here is the source of the nitrogen carrier gas. This is a cylinder of nitrogen. And we're controlling the flow rate of this nitrogen with these mass flow controllers. Here we are sending 2.5 standard liters per minute to the thermal desorption tube. Some of that flow of nitrogen is being overflown, and the rest is being taken by the SIMS this way through the thermal desorption tube. The SIMS takes around 2.1 SLPM. The nitrogen is then heated in the TT tube, and then it makes its way to the sample filter holder. Inside this filter holder, we have the filter, which had been collecting PFAS, or Philadelphia air, for around 2 weeks at a flow rate of 5.2 liters per minute. So our goal is that these nitrogen carrier gas, hot nitrogen carrier gas, is volatilizing the PFAS once it hits the sample. That volatilized PFAS is entering what's called the IMR, or ion molecule reactor. This ion molecule reactor introduces the iodide anion to all incoming species. Finally, here we are measuring the temperature of the thermal desorption tube using a thermometer. Here is an example of a sample filter. So, thank you very much. Appreciate it. So after showing you around the lab, I want to get into the experiment itself. I have a little section on background for PFAS for those interested, but I'm going to get into the details on the actual experiment. So we'll jump into the analysis. As you know, I set up a sample filter that collected a sample of aerosol for around 12 days at a flow rate of 5.3-ish liters per minute. And with that sample, what I did was I introduced it to the instrument. So in the plot in the middle on the left, it is a time series. It is showing the ions per second of both PFBA exact mass, which I suspect is PFBA exact mass, as well as the nominal mass 341. And there's 4 different sections here. The first section, it corresponds to the measurements during the sample holder, which also collected some aerosol because it was holding the filter. Then next was the sample, so the dirty filter. And the next 2 sections were repeated blanks. Below that plot, you can see another time series, and this just corresponds to the 2 blanks. My point in showing this plot here was that the 2 blanks were not consistent, and so we didn't establish a consistent background for this PFBA measurement, which is not good, and I'll get into that later. On the right, we have two characteristic peak shapes during 2 different times. So the first time is when I spiked the instrument with what I knew was PFBA. And weirdly enough, the PFBA gets even further buried than normal in this peak shape. And we have this big yellow one, which corresponds to either one of those 3 wacky compounds. And I don't suspect that those compounds were in our standard as impurities. So the only other option is what's going on is that something's wrong with the mass calibration. And that seems a little suspicious. On the bottom one, we have the characteristic peak shape for when we were actually measuring the sample. And so that one looks a little bit better. But it's still hidden under a bunch of other compounds. So in conclusion, we know that there's PFBA signal, or at least we suspect that there is. We can't reproduce statistically similar controls or blanks. As I mentioned, there's a little bit of an issue with the other compounds that are showing up around the same mass. And so resolving this PFBA peak seems to be a challenge. In literature, Rydell et al. Solved this problem by subtracting out background spectrums, but we can't really do that, as I mentioned, because we don't really have good background spectrums. And so mass charge 341 peak profile, so this nominal mass, this charge, this mass here that we've been talking about, it changes drastically when I was putting in that standard of PFBA. And so this is either because of impurities, which I don't think is the case, or it's from this mass calibration issue, which I talked about. But thank you very much for your time and listening to my poster. I want to thank my advisor, Dr. Wood, and our postdoc, Dr. Andrew Lindsay, for their incredible help and consistent guidance, and also for UREP for this grant. This wouldn't have been possible without you guys. I appreciate it.